Hello students. In this session, let us study the classification of optical fibers. Optical fibers are classified into three categories. First one, based on the materials used for making optical fiber. Second one is number of modes transmitted through the fiber. And the third one, the refractive index profile of the fiber. So here, classification is written. So materials used, there are two types when we consider the classification according to materials used: plastic fiber and glass fiber. So if you consider number of modes transmitted, there are two types again: simple mode and multi-mode. And if you consider the refractive index profile, so first one is step index and the graded index. Okay, based on the materials used, plastic optical fibers, the basic material is polymer. We know that plastic is a polymer, organic material. So the basic material is polymer. In glass optical fiber, the basic material is silica, that is silicon dioxide. It can withstand only low temperature. This can withstand high temperature. Highly flexible, moderately flexible, suitable for short distance communication system, suitable for long distance communication system. Durability is low, and here durability is high. Attenuation means the loss of energy or distortion is high here, and here attenuation is low. So you may get one of the concept questions: why glass optical fiber is preferred to plastic optical fiber, carrying 2 marks. So you have to write these three reasons. It can withstand high temperature, so it is, or you can write suitable for long distance communication system, durability is high, and attenuation is low. So now, as per based on the number of modes used, the single mode fiber. So what is single mode fiber? Wherein only single mode is transmitted. So for single mode, so we can use the core of smaller diameter and cladding of higher diameter, larger diameter. So this is classification based on number of modes used. So this is core diameter, so 8 to 10 micrometer. So this is lesser, and this will be larger, so 60 to 100 micrometer compared to this. And this is refractive index profile. So here this is the core refractive index N1, and this part is refractive index of cladding. So N1 is greater than N2. Okay, so here the N1 remains uniform throughout in the core, and it suddenly decreases at cladding and core interface, and it remains uniform throughout this cladding. So since this core diameter is lesser, so we can have a single mode here. So this is the acceptance cone. So a single mode is allowed. And for multi-mode, so this will be the diagrams for multi-mode. You see the core diameter is more here, so as to allow number of modes, and this is cladding diameter, and this is refractive index profile, and here we can have multi-mode. Okay, number of modes are entering within the fiber. So the source used uh, at the entrance, light source, LED or laser. That is, so you can write laser or LEDs are used as a source of the signal. Okay, these are the differences. So for single mode and multi-mode fibers. So single mode supports only one mode and multi-mode supports many modes. This core is surrounded by, thin core is surrounded by thick cladding. Here thick core is surrounded by thin cladding. There is no intermodal dispersion because only single mode is allowed. So intermodal dispersion is absent and hence no signal degradation. Here multi-mode is entered. So the number of modes are entered. So there is intermodal dispersion and hence signal degradation occurs. It is suitable for long distance communication, that is single mode, and multi-mode is suitable for short distance communication. Fabrication cost is high in single mode and fabrication cost is low for multi-mode. The difference uh, of refractive indices between the core uh, bet- okay, the difference between the refractive indices of the core and cladding is very small. Here the difference between the refractive indices of the core and cladding is large. Launching of signal is difficult here. Launching of signal is easier. So if you are asked to write the differences between single mode and multi-mode fibers, so you have to write 3 to 4 differences out of these 7 differences. Now, based on the refractive index profile, there are two types again. Step index optical fiber. Here the construction of step index optical fiber is similar to that of uh, this is not this, sorry. So in this fiber, the refractive index of the core is uh, uniform and throughout the core. Okay, the refractive index of the core is uniform and decrease suddenly at the cladding and remains constant again throughout the cladding, just like single mode and multi mode. So there will be step like profile. Okay, so this is the step like profile wherein n1 is more and n2 is less, so it remains uniform throughout the core and n2 remains uniform throughout the cladding. So this is uh, the geometry of the core and cladding or optical step index optical fiber. So here, so the diameter is 50 to 200 and here it is 100 to 250 micrometer. Now for graded index optical fiber, the geometry of green is same as that of step index multimode fiber. So this step index, it allows both single mode as well as multimode. So you can consider the multimode fiber for the geometry of graded index. It is also known as green. The diameter of the core ranges from 50 to 270 to 250 here. Okay. But the refractive index of the core decreases continuously. This is very important factor here. Refractive index of the core decreases continuously from the axis to the cladding and remains constant throughout the cladding. So the diagram is like this. You see here it is maximum at this point, it continuously decreases. Okay, it is dome like structure, continuously decreases and when it reaches cladding region it remains constant throughout the cladding. So n1 is greater than n2 but n1 decreases continuously, okay, within the core region. It is from the axis to cladding surface, it decreases continuously. Okay. Now we can consider, okay, so here the refractive index decreases continuously. So what this type of refractive index profile allows, it causes periodic focusing of light, okay, propagating through the fiber. So it is like this. So periodic focusing, you see, when it enters here optical fiber, the light from laser or LED. So you see ray 1 is here, or ray 2, let us consider first ray 2. So you see ray 2 traverses uh, lesser path, and ray 1 traverses longer path. Okay, so this is shorter path and this is longer path. So why it is traversing shorter path here? Because here it is denser compared to this. Okay, when the light traverses in denser medium, it moves slowly, and here, yes, yes, ray 1, this is rarer. Yes, no? Here it moves faster, hence it traverses longer path here, and here it is denser, it travels slower, so it traverses shorter path. Okay, so we can consider like this, the marginal rays, ray 1 in the above figure uh, travels longer path, mm, but are faster. Yes, no? As refractive index near the cladding is lesser. Yes, no? Near the cladding is lesser. So when the refractive index is lesser, it moves faster, hence it traverses longer path. If we consider the paraxial rays, that is ray 2 in the above figure, travels lesser path but are slower, as refractive index near the axis is higher, because here the medium is denser. We know that the refractive index decreases continuously. Here it will be denser, and at the end of the near the cladding, at the margin between cladding and core, the medium will be rarer. So this is the reason why we get focusing of all the rays at single point along the axis. Hence all the rays are focused at the same point simultaneously, and there is no signal distortion. So in green, either a laser or LED source is used to transmit the signal. So these are the differences between self-index fiber and graded index fiber. The refractive index of core is uniform. The refractive index of core decreases continuously from axis to the cladding, used for transmitting both single and multimode signals, used for transmitting only multimode signals. Intermodal dispersion is present, intermodal dispersion is absent. Light rays propagate in zigzag manner, just like in multimode optical fiber. Light rays propagate in helical manner. It is used for a long distance transmission. It is used for a short distance transmission. The refractive index difference between core and cladding is large. The refractive index between core and cladding is small. There is no focusing of rays in step index, but in case of graded index, rays are focused at the axis. Now let us study a derivation for uh, attenuation coefficient. So expression for attenuation coefficient: consider light traveling through an optical fiber of length L there will always be a loss in the intensity with distance traveled. Such a loss of intensity obeys Lambert's law. So Lambert's law, let us consider for granted. So what is Lambert's law? According to this law, the rate of decrease of intensity of light with distance traveled in a homogeneous medium is proportional to the initial intensity of light. So according to this, we can write minus dp by dl, where p is the initial intensity and l is the distance traveled. So this is the loss in energy. So uh, decrease in intensity. Okay, decrease in intensity with distance. So since it is decrease, we have considered as negative sign, and it is directly proportional to initial intensity. So if we consider an equation, let us write a proportionality constant alpha, and alpha is called the constant, alpha is the attenuation coefficient or attenuation. Okay, rearranging this equation by cross multiplying, we get dp by p is equal to minus alpha dl. So by integrating between the two limits, p is equal to p initial and the intensity p is equal to uh, p out, means when it emits out of the optical fiber. So initial p in and p out, we can write integration dp by p. So this will be ln p. So between the limits, so P in, P out. So this is ln P out by P in is equal to minus alpha L. So that will be P out, ln P out minus ln P in can be written as P out by ln P out by P in, according to the laws of logarithms, minus alpha L. So alpha is equal to this, we get this expression is the in terms of uh, ln, that is exponential logarithms. If you consider the decimal logarithms, that is log to the base 10, or it is known as common logarithm. So in the units of decibel per kilometer, we can write in terms of common logarithm by the equation. So alpha is equal to minus 10 by L log to the base 10 P out by Pn. Here the length of the fiber L must be expressed in kilometer because it is very larger value, so we have to consider in terms of kilometer. The factor 10 is introduced to express the unit in decibel. We know that one decibel means 1 by 10 bell. So the unit dB is chosen as loss of intensity is logarithmic in nature. Okay, from equation 2 here, from equation 2, why it is logarithmic in nature? It is resembling the human hearing response, or yeah, human hearing response when which has the same unit decibel. So common logarithm base is taken as 10 is used because in acoustics sound intensity is dealt in common logarithm. Okay, in acoustics always sound intensity, that is human hearing response of the sound intensity is dealt in common logarithm. That's why we have taken here common logarithm, and this 10 is for to convert that into decibel. Okay, so that will be decibel per kilometer. It is measured in terms of decibel per kilometer. So alpha is equal to what we have to write minus 10 by L log P out by P in. Okay, so let us end this session. Thank you.